Okay, well, start with the topic of hydrogen bonding, which we just touched yesterday. One of the very important forces stabilizing a protein in its native state, right? Because secondary structures like alpha helices, beta sheets, they all have hydrogen bonds, like intrahelical in case of alpha helix, or intrastrand in case of beta sheets. But before we talk about hydrogen bonds, though, there are two things we have to keep in mind. For example, hydrogen bond formation in a protein does not bring about a net gain in the number of hydrogen bonds formed, essentially because when you had the protein in the unfolded state, the groups that were making hydrogen, that are making hydrogen bonds in the stable state of the protein, or the native state of the protein, were also making hydrogen bonds with the surrounding water molecules in the unfolded state. So essentially they were still making hydrogen bonds. It is not that you are introducing a new system or a new condition where they start to make hydrogen bonds, they were already making hydrogen bonds. So the final stability is actually a balance, or it is determined by the difference, as it is said out here, in strengths of the aforesaid protein water and the protein hydrogen bonds. Okay. Now that is one. Now the next is, depending upon the protein in question, or any protein as such, your hydrogen bonds can be at different places. For example, you can have a hydrogen bond which is the surface of the protein, you can have a hydrogen bond which is in the interior, that is the core of the protein. If it is on the surface, then you can imagine it to be more exposed to the surrounding water molecules, hence it will be interacting with water. If it is in the core, then the obvious effect is that the dielectric constant in the core of the protein would be small, right, because it is essentially a non-polar core, and it might be that the hydrogen bonds, the strength of the hydrogen bonds, or even the length, as a matter of fact, would be depending upon where these hydrogen bonds are actually found inside a protein. So there was a very nice paper in Nature which talked about this effect, and what they said was, which we saw yesterday, that if you start from this very bottom, you can see that out here you have the soluble protein surface hydrogen bonds. Now these hydrogen bonds, they have an average distance of about 2.1 angstroms, 2.0 angstroms. Now when you go to the same soluble protein, but now you have hydrogen bonds which are buried. So I am talking about this now. You have buried hydrogen bonds. If you have buried hydrogen bonds, that means there the dielectric constant is low, and immediately what you see is the mean hydrogen bond distance has decreased to 2.02 angstroms. Now hydrogen bonds can still essentially be considered to be electrostatic type bond, hence if your dielectric constant is low, that means the screening between these two charges, or the electrostatic interaction, would be lower, and thus the hydrogen bond strength would be more, thus the distance of the hydrogen bond is lower. Now similarly, if you go to a membrane protein, so the bottom one is considered we are talking about a soluble protein. If you go to membrane protein now, membrane proteins typically would be in hydrophobic environments. For a membrane protein, if you talk about the surface hydrogen bonds, I cannot show you now, but the way it goes is these surface hydrogen bonds are oriented in such a way that they point towards the interior of lipid molecules. Okay. So these ones are more these ones are more towards interior of lipids. Lipids are the ones which actually constitute membranes. So lipids are highly nonpolar, and if you compare this to a protein core, in protein core you can still have some polar side chains or some polar amino acids, but in case of a lipid it is hydrocarbon tail, right, fatty acids, hydrocarbon tail, and that is why the dielectric constant in that case is the lowest among all the four, and you can see accordingly the hydrogen bond length is 1.98 angstrom, that is the shortest. And the last one is membrane protein buried hydrogen bonds. See, whether you are talking about a membrane protein buried hydrogen bond or a membrane protein or a soluble protein buried hydrogen bond, the hydrogen bond is buried, that means it is in the core of the protein, and the core of the protein in both the cases is essentially the same. So there is not much of a difference. That is why this buried hydrogen bonds and this bar hydrogen bonds in both membrane soluble proteins typically have the same mean hydrogen bond length. So, this is from I have taken this picture from this following reference given below. Okay. Now, what is the next discussion to be on? So, we have just seen the context dependence of hydrogen bond strength, but how can we prove it? To understand it, it is okay, it is easy to understand, but how easy it is to prove, or can we actually prove it? So, a group of researchers, essentially from the group of Jeff Kelly is at Scripps Research Institute. What they did was they did a double mutant cycle design, right, and we will discuss this at some length. So, they did two things. One was why is it called a double mutant, and if you look at this, it will be more clear in the next slide. There are two aspects. One is there was he did an amide to ester mutation. Now, if you look at this portion, so if you look at this portion, right, and say if you look at this portion, so I am talking about the hydrogen bond here, okay, I am talking about the hydrogen bond here, this one. So, this is all amide, that means you have NHCOs and all these things. Now, what they did was here, see this NH, this particular NH was replaced by an ester linkage O, and the moment you do that you lose H, right, because you do not have H now, and hence you can see you have disrupted the hydrogen bonding here, there is no hydrogen bonding here, right. So, that means here as it says donor is eliminated, you have no hydrogen bonding. So, this is you have disrupted the hydrogen bonding by doing an amide to ester mutation. Now, that was you have disrupted the hydrogen bonding, right. Now, the other thing is if you come down, you can see this R1 is being replaced by another bigger side chain R2. If it is a bigger side chain, a more hydrophobic side chain, what does it mean? That means R2 gives rise to a more non-polar environment than R1. So, here we are coming to a context dependence now, okay. And also on the same one R2 you do the same amide to ester mutation, and then you look at the thermodynamics. But what it means is, why is it called a double mutant? Because there are two mutants. What are the mutants? One is the amide to ester mutation, the other one is R1 going to R2, that is why it is called a double mutant, okay. So, it will be a little more clear in the next slide, we will zoom into it now. So, here, so again look at this, this is the one we are talking about, the hydrogen bond perturbation, right. So, we are perturbing the hydrogen bond by forming the ester, that is why it says donor eliminated on this side, right, and it says the acceptor is weakened, but let us not worry about the specifics, but look what they are doing here. So, this is important, this delta G, what is this delta G? So, this delta G 1 is equal to delta G F A 1 minus delta G F E 1. Now, F stands for folding free energy. We are not unfolding the protein, what we are doing is we are essentially looking at the difference in stabilities of the two proteins in their folded states, but in one case you have the amide, in the other case the amide is replaced by the ester, that is what you are looking at. So, that is one, right. Now, you can understand, so that is what delta G 1 is. If I go to the next slide, I do the same thing, but now in case of the amide what I have done is I have replaced R1 by R2, and then on that amide what I do is I replace this hydrogen bond again by an ester. So, I have R1 going to amide to ester, R2 going from amide to ester, again two mutants. In this case, what is the delta G2? You can see the delta G2 is essentially the difference in free energy between A2 and E2, E stands for the ester mutation, and this stability essentially comes from what? Mainly the hydrogen bond disruption. And if you look at this, if you go from, when you are going from R1 which is A1 to A2, That means, when you are going from A1 to A2, what are you disrupting? You are not disrupting in a hydrogen bond. Essentially, what you are tweaking with or playing with is the surrounding environment, the remember the micro environment we were talking about. So, that is why that is called delta G A. A stands for amide, and we are only sticking to amide, same amide, but we are replacing R1 by R2. And similarly, you can understand you will be having this delta G E on this side, right. Delta G E, E stands for the ester mutant, and also you are doing the same thing, you are replacing R1 by R2. Okay. So, that means you go to amide to ester, right, and also you go from amide to amide, R1 replaced by R2, also in the ester to ester, R1 is replaced by R2. So, essentially you have these parallel stuff coming out. So, just to make it a little more clear, what does this say? So, this slide says that A1 and A2 are all amide proteins, understandable. A1 is the one we started with, where we had R1, A2 is the one we had replaced R1 by R2, but A stands for amide, we have not done ester mutation. Now, obviously A2 has a bulkier hydrophobic side chain. So, whenever we talk about A2 under whatever context, A2 always resembles that R2 which is bulkier than R1. E1 and E2, as E stands for ester, these are amide to ester mutants, right. So, these mutations essentially we have removed the hydrogen bond of interest, okay, whichever hydrogen bond we are trying to probe here. And again, like A1 and E2, E1 and A2 will have the same side chain meaning. So, E1 corresponds to R1, the less hydrophobic or the less bulky one, E2 corresponds to R2 having the less bulky, I am sorry, more bulky R2. Clear the terminology? Okay. Now, let us look at thermodynamics. So, if you are talking about delta G1, as we briefly did in the other slide, so delta G1 is the folding free energy difference between your amide 1 and your ester 1, where 1 stands for R1. What have you done is you have disrupted the hydrogen bond. So, essentially it is this difference in free energy will come mainly from disruption of the hydrogen bond. Now, if you disrupt the hydrogen bond, we also start disturbing the structure. So, there are many other aspects that come into like solvation and all these things, but let us not worry about those, let us keep it very simple. Okay. This paper has talked about those aspects and said that those things really do not matter. Now, if you go to delta G2, delta G2 also is the same thing exactly like delta G1, only in this case R1 is replaced by R2, right. Now, what is delta GA? Delta GA reflects the effect of side chain on the folding free energy. So, delta G essentially is the delta GF A2 minus delta GF A1, you have not replaced any hydrogen bond, instead what you have done is you have replaced R1 by R2. I am repeating this so that you can make the connection always. So, this essentially is just because you are looking at a change in free energy where you have replaced a less hydrophobic, a less bulky side chain by a more bulky side chain, and the same thing is happening for delta GE. Okay. Now, look at the beauty of this approach. If delta G1 is not equal to delta G2, then the strength of the hydrogen bond is different based on the difference in side chains A1 and A2. And why do we say that? You look at delta delta G21. What is delta? Delta G is difference between 2, and delta delta G is the difference in delta G's, right. So, this delta delta G21 is essentially the difference in delta G's of delta G2 minus delta G1. What is delta G2? We know this from before, it is essentially delta G A2 minus delta G E2, and what is delta G1? It is delta G A1 minus delta G E1, this we have defined before. And if you do the math, you can see I can write this one as delta G A2 minus delta G A1, right. I can also write this one as minus delta G E2 minus delta G E1. So, that essentially comes to what? Delta G A and delta G E. Is this clear? Right? If you remember the previous, see this is what delta G A was, delta G A2 minus delta G A1, and delta G E was delta G E2 minus delta G E1, right, and that is what we have used here. So, the difference in delta G's, that means the delta delta G's essentially boils down to what? Delta G A minus delta G E. This double differential, essentially this delta delta G21 is referred to as the thermodynamic coupling energy. That means, if you see a difference, That means, if delta G1 is not equal to delta G2, it does not matter what the sign is of the value you are going to get. It means that because of that change in side chain, either R1, R2, R2, R1, you have brought about a change in the strength of the hydrogen bond. Essentially, that is what you are trying to prove by this thermodynamic cycle. Now, what experiment did they follow? So, this is the experiment they did. So, as I was saying, this delta delta G21, if it is less than 0, it signifies that the hydrogen bond that is perturbed by the amide to ester mutation is stronger in the microenvironment that is less polar, the latter being provided by the bulky side chain A2. Essentially, that is what is the outcome of your double mutant thermodynamic cycle. That is what they are trying to prove. Let us come to the actual experiment. What they did was, they did with a series of proteins, but let us stick with one, take one as an example. So, this is a protein, it is called a pin WW domain, you can see out here, it is a pin WW domain, and this is the one I am talking about. So, this is the protein, it is essentially beta sheet, right, not alpha helical, it is essentially beta sheet, and this is visible from this figure, right, is not it? You can see the beta strands, you can see this is one beta strand, this is one beta strand, and these two are intra bonded through hydrogen bonds, right, and these are the corresponding, you can see these are the corresponding hydrogen bonds, right. Now, which hydrogen bond are we going to perturb like the amide to ester? So, what they did was, so that is what this is the zoomed into portion, this is our probe part of the molecule of the protein. So, what they did was, you can see this is arginine 14. So, this is arginine 14, this is tyrosine 23. The arginine CO is hydrogen bonded to tyrosine NH. So, what they did was they replaced tyrosine by the corresponding ester. So, you have done the amide to ester mutation. Now, you look at this presence of valine out here. So, this is a valine. So, valine has this isopropyl side chain, and this valine is very close to the hydrogen bond. That is why they picked this hydrogen bond. So, if you are going to look at this contextual dependence, you need to have some amino acid or some amino acid side chain which is kind of bulky, provides a hydrophobic environment, and that is why they focused on this hydrogen bond. So, valine has this isopropyl group which kind of provides a non-polar environment to the hydrogen bond we were talking. Now, what they did was they replaced valine by the amino acid alanine. Okay, so, that means valine is now bulky, which is your R2, and when they replace it by alanine, it becomes R1. Okay. So, as it says, the hydrogen bonds are shown as thick dashed lines, as I just showed, and the hydrogen bond between arginine 14 CO and tyrosine 23 NH will be disrupted. Okay. Again, as we just discussed, the hydrogen bond is partially buried by the valine 22 side chain, because valine 22 essentially is hydrophobic. Amide to ester mutation done at tyrosine 23. The microenvironment now of the hydrogen bond is perturbed by mutating valine to alanine. That is the mutation you are doing. So, based on the terminology we had before, A1 should be the one where I have done the mutation. Why? Because A1 was R1 and R1 was the smaller one, which is alanine, right. So, that is what it says, A1 is valine 22 to alanine mutation, the mutation is referred to as V22A. That means, you have replaced valine at the 22nd position, which is the 22nd amino acid, by alanine. Then A2 is essentially your wild type protein. Wild type protein means the protein which is found in nature, just like that, but this is the one which has valine. So, this is R2, valine has a bigger side chain. Then when I do E1, E1 should correspond to A1, that means I am doing the corresponding amide to ester mutation on what? Not the wild type, but the V22A protein. isn't it, because that was my R1. So, when I do the Mi to ester mutation, that becomes my E1, and when I do the E1, you can see this E1 is this is what I am talking about. So, this is the one I am talking about. This E1 is called Y23 psi, where the tyrosine at 23rd position is replaced by the corresponding ester analog. That ester analog is represented by psi. Okay, that is the mutant. And then the E2 is Y23 psi mutation of the wild type valine 22. Okay, so essentially you can see you are going like this: V22A, then V22A Mi2 ester, then you have V22, then V22 Mi2 ester. Okay. So, this is the thermodynamic data. I will give you the values later. So, look, this is delta G1, right. So, this is delta G1 is this guy, right, for A1, and this is delta G1 for E1. Now, you remember what delta G1 and delta G2 were, right? Do you remember what delta G1 and delta G2 were? So, go back. So, this needs a little bit of tweaking. So, delta G1 was delta GA1 minus delta GE1, right, and delta G2 is delta GA2 minus delta GE2. Okay. So, what now they are doing is, this is the corresponding delta G for A1, this one. So, this is the corresponding delta G for A1, and this one is the corresponding delta G for E1. Okay. And if you take the difference between delta G A1 and delta G A1, what do you get? You get delta G 1. Similarly, on this side you can see you have the delta G F. Remember, everything is the folded. This is delta G F for A2 and this is delta G F for E2, and the difference between these would give you what? Delta G 2. And obviously, now since you have got delta G 1 and delta G 2, finally that difference will give you what? Delta G 2 1. You know, that is the one you are going for, to see whether the hydrogen bond has any contextual dependence. Okay, let us look at the values now. So, delta G2, you know, they have done these experiments. Delta G2 is minus 4.23 kilocalories per mole, right. Now, this points to a significant decrease in folding free energy upon A to E mutation. Now, that is understandable. Why is it understandable? Why is it understandable? Because you have disrupted a hydrogen bond. Hydrogen bond is necessary for the stability of the protein. When you disrupt the hydrogen bond, even if you are disrupting one hydrogen bond, possibly it is a major hydrogen bond, major in terms of the structural preservation, and hence you have disrupted it, and that is why you can see the delta G gives rise to so much of a difference. Okay. Now, this is a huge difference, take it from me. Delta G1 also the same thing, but it is minus 3.06. Now, see, in both the cases you have disrupted hydrogen bonds, is not it? Delta G, what is delta G2? It is essentially delta GA2 minus delta GE2. What is delta G1? It is essentially delta GA1 minus E1. What you are looking at is, you are not looking at between A2 and A1, what you are looking at is between A2, E2, A1, E1. If in both the cases the hydrogen bond strength had been the same, that means the extent of disruption would have been the same, then delta G1 would have been equal to delta G2, is not it? Because you are disrupting a hydrogen bond, you are doing nothing else. Now, do not worry about the side chains. What essentially you are doing is just disrupting a hydrogen bond. You do not have this thing in mind that hydrogen bond might be contextual, might be having a contextual dependence. That means a dependence on the surrounding environment. If you do not have that in mind, what you would think is, okay, if I am going to disrupt a hydrogen bond, I would expect delta G1 to be equal to delta G2, as simple as that. Clear? But obviously, this is not the case. You can see there is a distinct difference. And why does this difference come in? Because you have replaced valine by alanine or the other way around. So, what this is saying is delta G2 minus delta G1 is minus 1.17 kilocalories per mole. Now, what was the 2? A2 was essentially the valine one, right, the wild type. This is the one which has the more hydrophobic side chain. So, it immediately tells you if the difference in free energy is negative, that means that mutant, in that mutant, or not that mutant, in that protein, let us talk, the hydrogen bond is actually more stable than the other one. And why is it more stable? The only reason it is more stable because you have a hydrophobic, your microenvironment is more hydrophobic for the valine one as compared to the one where you have mutated valine to the alanine. Okay. So, this is a direct evidence of your hydrogen bond being dependent upon its microenvironment. Now, remember, when I talk about its microenvironment, I am not talking about the whole environment. I am talking about micro means very small, that means very close to where the hydrogen bond is, because if you are doing some perturbations which is far apart from the hydrogen bond, it might not feel its effect that much. Hence, you have to be very close. This is why it's called the microenvironment. Okay. So, again the drive home point of this is, yes, hydrogen bonds are necessary, because you have seen if you disrupt hydrogen bonds, you have this change in free energy, right. So, that is what we saw last slide. See, if you disrupt the hydrogen bonds where delta G A2 minus delta G E2, that means delta G E2 is less stable, right, which means hydrogen bonds are important. Not only that, you will also have to consider what are the nearby side chains, the side chains which are proximal to the hydrogen bond, because that will also finally determine what the strength of your hydrogen bond is, right. So, having said this, this brings us to the end of our discussion on the forces involved in protein folding. Now, whenever I would take any specific case, I would actually maybe come back to this or give you some more examples related to this, but right now we have already spent a lot of time on forces in protein folding. So, let us move on now. What do these forces in protein folding finally give you? These forces in protein folding finally make sure that when you move from a folded from an unfolded state to a folded state, that the protein remains folded, right. When if you are talking about this difference in free energy between the folded form of the protein and the unfolded form of the protein, what you are talking about is the protein stability, because the protein can only be stable if there is a decrease in free energy when you go from the unfolded to the folded form. So, that is the next topic of our discussion, which is protein stability curves. Now, what do I mean by a protein stability curve? What I mean is this: the stability curve of a protein is defined as the plot of the free energy of unfolding as a function of temperature. Again, it is the plot of the free energy of unfolding as a function of temperature. That means, what am I looking at? I am looking at the free energy of unfolding, which is given by delta G. Okay. I can write this delta G as, well, I will just keep it like this, n to d, I will tell you what n and d are, is equal to G of d minus G of n. What is d? D stands for denatured and n stands for native, and that is why it is called the unfolding free energy, right. I am not looking at the reverse, I am trying to unfold the protein, and that is the cost, the free energy I am looking at. And if you plot that free energy as a function of temperature, that is your stability curve. Now, this is something you have seen before, but now we will kind of look at it in a little more detail. So, look at this delta G. This is actually your molar Gibbs free energy, you can understand, right, it is kilocalories per mole. So, whatever we are going to talk right now is essentially molar Gibbs free energy. I am just not going to write any in a symbol or try to specify anything else by any symbolism, that is molar Gibbs free energy or molar enthalpy or molar entropy. Everything is essentially molar we are going to talk about. Now, see this line, is your stability curve. What are you looking at again? You are looking at delta G unfolding, right. That means G d minus G of n. You look at the temperature, this is going from 0 to 100, and look at how the curve goes. How does the curve go? You see the curve goes from here, it maximizes. So, this is the maximum of the curve somewhere here, maximum of your stability curve, and then it again comes down. there is one more important point. Point is, you look at these two temperatures. These two temperatures are those points where delta G is what? Equal to 0, right? If your delta G is equal to 0, see, if your delta G is equal to 0, what do you mean? Equilibrium. In that sense, if your delta G is equal to 0, you do not have any preference for any of these, right? Your delta G is 0, there is no free energy difference between Gu and Gn. That means either one should be present, and that too present in equal bias. You have no bias, right? That means equal concentration, and if they are present in equal concentration, that means K is equal to 1, and hence delta G is equal to 0 for that, because delta G is equal to, or delta G naught is equal to minus RT ln K equilibrium. So, when you have an equal amount of folded and unfolded molecules, that is native or denatured protein molecules, those points are referred to as your melting temperatures. So, melting temperatures are those points where you have equal concentration of unfolded and equal concentration of folded protein molecules, right. But that is not the only thing. When you think about, see, this plot is of gives free energy as a function of temperature, isn't it? So, when you think about trying to disrupt a protein structure and going to the unfolded state or the denatured state from the native state, what are you essentially doing? You are putting in thermal energy because increasing temperature, and you are destroying, and that is understandable. And that is why you can see at the higher temperature you have a Tg, right. There is a Tg at the higher temperature, this corresponds to somewhere close to 60. That means you have a melting point for this protein, the melting point or the Tg, G is for transition. If you remember, Tg refers to that point where delta G is equal to 0. Okay. So, let me write that. Tg refers to that point where delta G is equal to 0. This is very similar to two other temperatures. Do you remember what we two other temperatures we discussed before? Th and Ts. So, Th was defined as the one where delta H is 0, Ts was delta is 0, and obviously then Tg means delta G is equal to 0. And the moment you take delta G is equal to 0, that means you are talking about the midpoint, thermal melting midpoint. So, obviously this the higher end Tg is your high temperature, that means you have increased the temperature, you have disrupted the protein and you have started melting it. But you look at the shape of the curve is crossing the 0 line at 2 points, one is Tg and the other one is Tg prime. So, this Tg prime, write it here, this Tg prime is referred to as the cold denaturation midpoint. It is a little hard to think, right? We always think of proteins being disrupted when we increase the thermal energy, but we never think of the reverse. That means we are going to, when you are going to decrease the temperature, you are also going to unfold the protein. That is why this Tg prime is referred to as the cold denaturation midpoint. So, proteins will have the tendency to undergo cold denaturation. In other words, if you would decrease the temperature a lot, the protein would undergo cold denaturation. It is just so evident from this stability curve, because it just crosses the delta G is equal to 0 at 2 points. Okay. One more thing, you look at this Tg prime, what do you think is the approximate temperature it is coming here? It is coming at less than 0, right? Right, less than 0. See, normally it is in degree Celsius, right. So, normally when you do your protein unfolding temperatures, you say you essentially look at it say from 5 to 90, 95, whatever. Okay. You cannot go to 100 and above, because water will start boiling anyway. But what it says is that if you have to look at the protein which is getting denatured in the cold form, that means at a low temperature, for this protein I have to go to a temperature which is below 0. If you are not going to go to below 0, you are not going to absorb what? You are not going to absorb that Tg prime. Okay. Well, there are other ramifications of this, there are other meanings of this. Depending upon the protein, this Tg prime can be below 0, can be above 0 and all these things, but at least the take home point of this is the stability curve gives you 2 points of denaturation. One is a heat induced denaturation and the other one is a cold denaturation. So, T g is heat induced denaturation, T g prime is your cold denaturation. Please keep that in mind, and this is so evident from the stability curve. Okay. One more thing, you look at this delta H and T delta S, right. This T H and T S we had seen before, but look at the slopes. The slopes are really steep, isn't it? The slopes of delta H and T delta S curve, these are really steep. Why is it so? Because we are talking about a protein and the change in what? Heat capacity, delta Cp is really high, and that is why the slopes are so steep. Okay. Let's move on. So, let us recall the thermodynamic equations. These thermodynamic equations we derived before when we are talking about the hydrophobicity, right, the hydrophobic effect, and we will come back to these again. The curvature, this is also what we have looked at before. The curvature, which is del 2 delta G over del T squared, is equal to minus delta Cp over T. So, the curvature is defined by your change in heat capacity, and the slope of the curve is given by the change in entropy, that is del of del G over del T is equal to minus delta S. Now, this we know. Now, where do we go from here? So, where do we go from here? Let us actually now go to pen and paper and start deriving some basic thermodynamic equations. So, by definition, the melting or transition temperatures are those for which delta G is equal to 0, right, because when the transition is occurring, that means where you are at T g and T g prime, delta G is equal to 0, that is what it means. So, T g is the high temperature transition point, and T g prime is the low temperature transition point. And this refers to cold denaturation of a protein. Okay. This refers to cold denaturation of a protein. Now, this is important. Now, let us see what we know based on this midpoint. So, let us look at focus on T g. Okay. Let us focus on T g. At T g, well, I know from my Gibbs-Helmholtz equation delta G is equal to delta H minus T delta S, right, this is known to us. Now, when we are considering T g, that means at T g, I can write delta G T of G is equal to delta H T of G minus T g delta S T of G. Now, what I will do is I will just make a small change in symbolism. I will say delta T of G is actually delta G G, delta H T of G is delta H G, delta S T of G is actually delta S G. So, these are the symbols I will be using henceforth. So, this we know, okay, it is not a big thing, but along with this what we also know is at T of G delta G of G is equal to what? 0. Excellent. So, what we have is then what we have delta H G is equal to T G delta S g, right, or we have a relation for T g in terms of delta H g over delta S g. Okay. This is equation 1. That means your transition temperature where delta G is 0 is essentially equal to the change in enthalpy over the change in entropy. Good. Now, T g, how is it determined? It is essentially the midpoint. It is essentially the midpoint of your calorimetric or spectroscopically determined transition. Now, what I mean by this is not immediately clear to you, but just keep this in mind. We will come back to this very soon. So, if you ever look at a protein depending upon what type of protein it is, it will always exhibit a transition from the folded to the unfolded state. You have heard about the word cooperative, right? Either it is a cooperative transition or non-cooperative transition. Essentially, that is what it talks about, the nature of the transition, and we take the midpoint of that. Now, delta H g can be determined calorimetrically. So, what we have done is, based on equation 1, you can see, based on equation 1, I already can determine T g, I can determine what, delta H g. So, then what can I find? Using these I can find delta S, right. So, then use to find delta S g, straightforward. Now, let us look at this again. So, remember, now we are focusing on delta H, okay, we are focusing on delta H. Now, remember this, delta H at a certain temperature T was given as delta H T 1 plus delta C p T minus T 1, where I said T 1 is a reference temperature, is not it? Where I said T 1 is a reference temperature. Now, let me do this. This equation is valid for any pair of temperatures. So, this equation is valid for any pair of temperatures. It does not matter what T and T 1 is, right. T 1 can be any reference, T can be any temperature that I am doing that I am interested in. So, what I will do is, in this case, what I will do is, I will say that T 1 is equal to T g, T 1 is equal to T g, and the temperature I am interested in, T, is equal to T of H. See, T g is what? T g is the transition temperature. Now, why I am taking T g to be the reference one? It is very simple, because if I look at a protein, if I look at a spectroscopic transition of a protein or any calorimetric experiment, I can easily figure out where what my T g is, because it is what? It is the midpoint. So, if I have a transition something like this, I can, if I have a transition, I will show this to you later, I can easily kind of locate where the midpoint of the transition is somehow, and then hence I know T g easily. That is why T g is always the easiest reference temperature, right. And then I say, okay, I also know what T h is. The T h has a significance of what? The delta H at that point is 0. See, I am trying to get some relations. So, then based on this, I can rewrite as delta H T of H is equal to delta H T of G plus delta Cp. Now, this T is Th minus T of G, clear. So, for me T1 was Tg and for me again T is Th, but based on the definition of Th, what do I know? This is equal to what? 0 based on definition of Th. Hence, what do I have immediately? I have that delta Cp Th minus Tg is equal to minus delta H T of G, or I can write T of G minus T of H is equal to, see I have reversed the order, I have taken care of the sign, is equal to delta H, I write delta Hg over delta Cp. Say, so this would be what, equation number 2, I guess. So, what have you done now? What you have done is, you know what the equivalence of Th is, you know what the equivalence of Tg is, and you have managed to relate this Tg and Th by what? Through delta H and delta Cp, both of which can be measured, both of which can be experimentally found. Okay. Good. Now, let us do the same thing with entropy. So, let us look at delta S. So, what was delta S for me? Delta S at a certain temperature T was equal to what? Delta S, I said T2, right, plus delta Cp natural log T over T2, was not it? That is what we had before. Okay. Now, I say T2 again is equal to Tg, because that is my reference temperature, and T is equal to what? Ts. Okay. So, therefore, I have delta S, I can write Ts is equal to delta S Tg plus delta Cp natural log, and look at this, this T is Ts by Tg. Okay. Again, by definition, what happens to this guy? This is 0 by definition of T of S, clear. So, based on this, I just go one more step and say that delta S T of G is equal to minus delta Cp natural log T of S over T of G, or I can take care of the negative sign and write natural log T of G over T of S is equal to delta S G over delta Cp. This should be equation 3. Clear? So, now what you have done? One, you had a relation between Th and Tg. What does this equation give you? This equation gives you a relation between Ts and Tg now. So, you see you have 3 major temperatures, one is Tg, the other one also is Tg prime, well, but let us talk about Tg. You have Tg where G is equal, where delta G is 0, you have Th where delta H is equal to 0, you have Ts where delta S is equal to 0, and you have managed to relate those two pairwise through these two equations. Okay. Good. Now, this is one set of equations. Now, let us do one more thing. Let us go back to delta H again. So, for example, delta H, I know T, I will always start with this, is delta H T1 plus delta Cp T minus T1. Now, what I do is I say let T1 be T of H. let T1 be T of H and T equal to, can you say what it will be here? Huh? Ts, yes, Ts. If I have that, then I can write delta H Ts is equal to, this delta H T of H would be what? Let me write it again, T of H, this is 0 plus delta Cp, then Ts minus T of H, okay, or I can write T of S minus T of H is equal to delta H T of S by delta Cp. So, this is equation 4. Okay. Now, can someone tell me the importance of this one, this equation? See, the other two we had related what? Th to Tg, Ts to Tg. In this case, what you have related? You have related Th to Ts. Why? Why do we need it? Huh? Tg can be calculated, okay. There is one more thing. Tg can also be calculated from the other ones, but there is also one more thing. What was it? Huh? Well, not exactly. Think about this. What was the main difference between your, these delta H T delta S curves for a hydrophobic molecule, say neopentane, as compared to one where you have protein? What was the main difference? Ts minus Th, right? And we said that in case of a protein, the Ts minus Th was very close. I mean, they are very close to each other, but it was far apart for a hydrophobic molecule. So, if we can somehow get a relation between Ts and Th in terms of thermodynamic parameters, it will be easier for us to reason out why. Now, this is what will lead us to that. You can see Ts minus Th is equal to delta H Ts by delta Cp. Now, what do you mean by delta H Ts? What do you mean by delta H Ts? At Ts, what happens to delta S? 0. Okay. Therefore, I can write delta H T of S, yes, I can say is delta H S, right. This is equal to what? Delta G S, isn't it? Because delta G is equal to delta H minus T delta S. Delta S is 0 for you at T of S. So, delta G is directly equal to delta H S. So, then what will happen is T S minus T of H is equal to delta G of S by delta Cp. This is number, this is what, number 5, I guess. Okay. So, here the magnitude of the difference between Ts and Th is directly correlated with the ratio of the change in free energy over the change in heat capacity. Now, let us try to see why this Th and Ts are so close to each other for a protein. Yeah. Look at this, the delta Cp for unfolding. So, this is what we derived just now. Now, the delta Cp for unfolding is large and falls in the range of 12 to 18 calories per degree per residue. This delta Cp. The maximum stability of protein is, however, not that high. It is only of the order of 50 to 100 calories per residue. It is not high at all. Typically, for proteins, the stability ranges from say 5 to 10 to 20 kilocalories per mole, which is not high by any standards. So, that means if your delta G is not high, but if your delta Cp is very large, what happens to the difference between Ts and Th? It becomes small. And essentially, that is why, so for proteins, delta Gs is small, delta Cp is large. Hence, Ts is very close to Th, or Ts minus Th is very small. This is why derivation of this relation was so important. Second, based on this, can you rationalize the huge difference in Th and Ts for a hydrophobic molecule like neopentane? Delta Cp is very small. See, for a hydrophobic molecule, if you remember the comparison, when we were taking neopentane in water, the delta Cp was like 363 or 368 or something like that. But neopentane, in neopentane, like gas neopentane in liquid neopentane, the delta Cp was what? 38, 40 exactly. It's a huge difference. From that, make sure of the fact that this Th and Ts for a hydrophobic molecule are far apart from each other. Okay, so that is where a protein is so different from a normal hydrophobic molecule. Okay, so this is about Ts and Th. Let's look at some. Don't know how much time we have for today. Oh, okay, already we are out of time. But I think we'll stop here. But before stopping, I just forgot to tell you one thing. Let me mention that or stress that point. Okay, see, we talked about this, right? We talked about this. Okay, we talked about this Ts minus Th, right? So we talked about this Ts minus Th being equal to delta Gs over delta Cp. That's what we talked about. Now what we can do is, this gives rise to something known as a triangular relationship. This gives rise to something known as a triangular relationship, and if you would look at it, it's not coming there, I guess. So what the triangular relationship will look like is, I can draw this, or it's there. Okay, we can draw it. The way we can draw is this. You can see this is Th. Here you have Th, right, and you have Ts, and this is your delta G. It almost looks like a triangle, and this is the triangular relationship we are talking about. And this triangular relationship is maintained obviously for proteins, and that's what the relation we have derived. So this also, you can see this we had described. This one was the point where you have the maximum stability. And where do you have the maximum stability? We have the maximum stability where it corresponds to Ts. And what happens to Ts? Your entropy is 0. So essentially, a maximum stability arises mainly from the difference in what? Enthalpies between the folded and the unfolded states, or denatured and native states, right? Again, please keep this in mind. This is called a triangular relationship between Ts minus Th and delta G. Okay, and this serves to be a very important way of trying to rationalize why, in case of proteins, Th and Ts are so close to each other. Okay, so we'll stop here, and from next class we'll start with some more thermodynamics with relation to protein stability.